Hi everyone, I'm Binchen from UC Riverside. Today I'm introducing our work on using just one proxy device for hardware-aware neural architecture search. This is a joint work with University of Notre Dame. Let's start with the fact that convolutional neural networks have been deployed on increasingly diverse devices, including mobile, ASIC, and edge devices. On such platforms, model performance such as accuracy, latency, and energy consumption are important metrics to consider. Therefore, as a key design hyperparameter, it is crucial to optimize the model architecture. Neural architecture search when NAS has been proposed to efficiently automate the design of neural architectures. A typical process of NAS starts with a search strategy selecting an architecture from a predefined search space. Then the architecture is passed to a performance estimation strategy, which returns the estimated performance back to the search strategy. Many prior NAS algorithms can be categorized as NAS without a supernet. That is, given each candidate architecture produced by the controller, the model is trained and then evaluated for its performance, based on which the controller produces another candidate architecture. The search cost of this type of NAS can take up to 100 GPU hours for even a single device. In view of the extremely diverse devices and platforms for model deployment, one-shot NAS has been proposed by utilizing the weight-sharing mechanism. The key idea is to decouple model training from the search process. That is, we first pre-train a supernet and then use a separate search process to discover optimal architectures that inherit the weights from the supernet. While pre-training the supernet is more costly than training an individual network, the training cost is one time for each learning task. For example, with the recent once-for-all algorithm, the amortized training cost for each target device is around 12 hours. With a order of one model training cost incurred by one-shot NAS, the cost of performance evaluation increasingly becomes a bottleneck, which is the focus of this work. To reduce the accuracy evaluation cost, state-of-the-art NAS algorithms have leveraged the accuracy predictor. That is, we first measure the accuracies of sample architectures and then build a machine learning model. Then the candidate architectures can be ranked based on their predicted accuracies, speeding up the NAS process. The accuracy predictor is device independent and can be reused for different target devices, incurring a fixed one-time cost of one of one. To reduce the latency evaluation cost, latency predictors have been commonly used. That is, profile the latencies for sample architectures in advance and then build a latency predictor. Since the total number of candidate architectures sampled by a NAS algorithm is typically in the order of 10K or even more, the total latency evaluation time would be 50 hours for one target device. Alternatively, flops can be used as a device agnostic proxy, but it cannot accurately reflect the true latency rankings of different architectures on a target device. When we summarize total search cost of a few representative hardware-aware NAS algorithms given n target devices, we use CT, CA, CL to denote model training cost, accuracy evaluation cost, and latency evaluation cost respectively. We can see that the latency evaluation cost is the dominant part, especially when n increases. In practice, the target devices for CNN deployment are extremely diverse. For example, even for the mobile devices alone, as shown here, there are more than 2,000 system-on-chips available in the market, and the only top 30 system-on-chips can each have over 1% of the share, which means in practice, n would be extremely large. In this paper, we focus on reducing the total latency evaluation cost for scalable hardware-aware NAS. Specifically, we show that building a latency predictor for just one device, rather than for each individual target device as in state-of-the-art, is enough. The general problem of hardware-aware NAS can be formulated as finding the optimal architecture X in the given search space that maximizes the accuracy while meeting the latency constraints, which is also called the Pareto optimal model. Since the inference latency is highly device-specific, with a new device, the latency function will change, and so will the Pareto optimal architectures. So achieving order of one latency evaluation cost may seem very unlikely. Our insight is that if latency functions of two devices are monotonic, their parallel optimal architectures can actually be identical. Let's see the definition of latency monotonicity first. Suppose we have two devices, D1 and D2, and two neural networks X1 and X2. Suppose X1 is slower than X2 on device D1, and X1 is also slower than X2 on device D2. If this relationship holds simultaneously for any two neural net architectures in the given space, then we say that devices D1 and D2 satisfy latency monotonicity. Then let's see how latency monotonicity among devices can be applied to hardware-aware NAS. Define AD1 as the set of architectures satisfying latency constraints on device D1. Then with latency monotonicity, we can find another latency constraint LD2 on device D2 such that AD2 is the same as AD1. Latency constraint on device D1 is equivalent to latency constraint on device D2. Therefore, the formulation here for devices D1 and D2 are equivalent, sharing the same set of parallel optimal architectures. To quantify the degree of latency monotonicity in practice, we use the metric of Spearman's ranking correlation coefficient, or SRCC. The greater the SRCC of model latencies on two devices, the better the latency monotonicity. Here we randomly sample 10K models from the MobileNet V2 space and measure their latency on 4 tablets. In the left figure, x-axis is the model latency on Samsung Galaxy Tab A, y-axis is the model latency on the other 3 devices. Heatmap on the right figure quantifies the latency monotonicity between these 4 devices. You can see that the SRCC between any 2 devices is close to 1. And usually SRCC of 0.9 to 1 is viewed as strongly dependent. Besides mobile platforms, we also measure these 10K models on other platforms including desktop GPU, CPU, and FPGA to illustrate that flops is not an accurate proxy for actual latency. I will also show the SRCC between flops and the latency measurements on these devices. Previous results are for devices within the same platform. Then how about the cross-platform case? In the right figure, S5e is a mobile tablet, 4790 is a desktop CPU, and Tesla T4 is a desktop GPU. It can be seen that latency rankings are only moderately correlated for cross-platform devices. The SRCC values are lower than the case of mobile device pairs, since mobile devices often differ significantly from desktops or FPGAs. To explain the empirically observed latency monotonicity, we utilize the Roofline analysis, which is a methodology to represent hardware platforms' peak performance as a function of the operational intensity. When operational intensity is low, memory bandwidth is a limiting factor for program speed. When operational intensity is high, peak flops rate becomes the bottleneck. Suppose we have two models X1 and X2 in the memory bound region of device D1, and X1 is slower than X2. Then we have the left side of the equation here, and then we multiply both sides by bandwidth of device D1 over device D2. Then this relationship also holds for device D2. That is, model X1 is also slower than model X2 on device D2. When two models are both in the compute-bound region of a device, a similar logic can apply to analyze the latency monotonicity. The Roofline analysis only provides a sufficient condition for latency monotonicity under the assumption that devices run at their peak performances. Next, we experimentally show the actual performance of CNN models on our 4 mobile devices. We measure the actual attainable peak performance of our 4 devices with gables. We see that the reach operational intensity of 4 tablets are all around 2 flops per byte, while the operational intensity of our sampled models are in the range of 2.6 to 5.4 flops per byte. So most of our sampled models are in the compute-bound region of these devices. This partially explains the strong latency monotonicity that we empirically observe in the mobile platform. Our previous results demonstrate the existence of latency monotonicity among devices within and across platforms. Here we show the flow of using this property to hardware-aware NAS. The prerequisite step is to select a proxy device and run state-of-the-art hardware-aware NAS to find a set of parallel optimal architectures for the proxy. Given a new target device, we first check its latency monotonicity with the proxy. if the SRCC is higher than 0.9, which means strong latency monotonicity is satisfied, and we can directly reuse the same set of Pareto-optimal architectures with the proxy. If the latency monotonicity is not strong enough, we will need to measure latencies of more models on the target and perform proxy adaptation until the SRCC reaches 0.9, and then perform NAS with the adapted proxy. I will explain the major components in the next few slides. For a given target device, the first step is to reliably estimate its SRCC with our proxy, because the cost will be too high if we need to measure the latency of a lot of models on the target. Here we show that latency measurement based on a few samples is enough to reliably estimate the SRCC value. Each curve here denotes the SRCC value between a pair of devices. X-axis is the number of models we randomly select from the search space. Y-axis represents the mean SRCC value and standard deviation calculated on the selected model set. For example, for all the device pairs we measure here, basically 30 to 50 sample architectures are sufficient for the SRCC values to converge. So the cost of measuring latencies for the small set of sample architectures is negligible compared to building a device-specific latency predictor. The next question is what happens when the latency monotonicity is not high enough between target and the proxy. In our experiment, we empirically set 0.9 as the threshold, let's say y. In this figure, we show the final Pareto-optimal models searched with proxy's latency predictor when SRCC threshold is not met. Specifically, we use Samsung Galaxy S5e as the target, and a desktop CPU with SRCC 0.78 and desktop GPU with SRCC 0.72 as proxies, respectively. Architectures searched on these two proxies are highly suboptimal compared to those searched specifically on the target. So when latency monotonicity does not meet the threshold, we cannot reuse the Pareto-optimal architectures found for the proxy device to a new target device. To address this issue, we propose an efficient transfer learning technique. Suppose X is the architecture representation and W is the weight of the proxy's latency predictor, and we have a few latency measurement samples on the target device, denoted by Xi, Yi. Then we can adapt the proxy device latency predictor to the target device by solving the optimization problem here. So essentially, we construct a new virtual proxy device, and our goal is to increase the latency monotonicity between the new virtual proxy and the target device. Here we show the effect of our proxy adaptation approach. As highlighted, the original SRCC between Pixel 3 and other devices or models in the NASBench 201 search space are pretty low, while after adaptation, the SRCC values are boosted to close to 1, which satisfies our threshold of 0.9. For experiment setup, we consider several search spaces including MobileNet v2, NASBench 201, FBNet, and NMeter proposed in a recent paper. For the MobileNet v2 space, we perform a one-shot NAS search strategy with evolutionary search, and a supernet provided by Once for All. For search space whose candidate models have released accuracy and latency measurements like NASBench 201, we perform exhaustive search alternatively. Our baseline for one-shot NAS experiment is heuristic scaling inspired by MNASNet and EfficientNet. The searched architectures are evaluated on ImageNet validation dataset for accuracy. Here we show the result of one-shot NAS experiment in the MobileNet v2 space, with one of our mobile devices as proxy and the other three as target. As introduced previously, the SRCC among them are close to 1, which is extremely high. So the architectures searched with proxy almost overlap with the optimal ones on the target device, while the baseline heuristic scaling can result in really bad architectures without performance guarantees. Then we show the result for non-mobile devices. Since these devices will have low SRCC values with the proxy, we use the previous adaptation approach to create a virtual proxy device, which has SRCC of at least 0.9 with the target. We see that with a low SRCC, the architectures searched on the proxy are not parallel-optimal on the target device. With proxy adaptation, the SRCC increases significantly, and the architectures searched on the adapted proxy are almost the same as those directly searched on the target device. This highlights the need for strong latency monotonicity between proxy and the target device, as well as the effectiveness of our proposed proxy adaptation technique to boost the latency monotonicity. Next, we show exhaustive search results out of 10K randomly sampled architectures in the MoveNet V2 space, using the predicted accuracies as the true values. We see that due to the low SRCC, architectures found by using the proxy's latency predictor may not overlap with the Oracle's Pareto-optimal boundary. On the other hand, with improved SRCC, the architectures found by using the adapted proxy's latency predictor preserves Pareto optimality very well on the target devices. We also evaluate our approach on the recently released latency datasets for 6 different devices in NASBench 201 space. These figures show the optimal architectures found by using the proxy device latency predictor, the adapted latency predictor, and the Oracle respectively. For example, the first figure shows that some of Pixel 3's optimal architectures deviate from the Pareto optimal boundary on the edge GPU by using proxy adaptation and increasing the SRCC values. The adapted proxy's optimal architectures can be efficiently transferred to the target devices while preserving optimality. Some takeaway messages we would like to share are that first, latency monotonicity exists among devices, both intra and inter-platform, and we can use just one proxy device latency predictor for NAS on different target devices. For the practical cases where latency monotonicity is not high enough, it can be boosted by adapting the proxy's latency predictor to the target device. And these approaches altogether keep the hardware-aware NAS cost at order of 1, while without losing optimality. And for more details and results, please refer to our paper and source code. Thanks.